A Blinky-Lite case study. The Fermilab IARC Compact Superconducting RF Electron Accelerator. Particle accelerators are transitioning from esoteric big science facilities to compact commercial applications. Thanks to groundbreaking developments in superconducting radio frequency technology at Fermilab IARC near Chicago, Illinois, one promising application is accelerators for medical sterilization. During manufacturing, many medical devices and equipment used on humans, including gowns, surgical drapes, syringes, and implantable devices, must be sterilized. The U.S. has a huge, regulated medical device sterilization industry, which is expected to grow considerably. However, experts say the most common sterilization methods are unlikely to handle this continued growth. The industry is urgently searching for alternatives because the two leading technologies are ethylene oxide and cobalt-60, which both present safety issues. X-rays provide equally effective penetration as a powerful alternative to gamma rays produced by cobalt-60. X-rays can be produced by electron beam accelerators, which do not generate the residual waste associated with cobalt-60. However, current accelerator technology for producing intense X-rays is not energy and cost-efficient. The Fermilab IARC team is addressing this issue by developing a new, efficient electron beam accelerator system using superconducting radio frequency cavities to accelerate particles, significantly boosting energy efficiency. Typical niobium SRF cavities require liquid helium for cooling to maintain superconductivity, which adds bulk and cost. However, the Fermilab IARC design innovatively uses commercially available cryogenic coolers, similar to those used in MRI machines, instead of a liquid helium bath. The challenge with these smaller coolers is to keep the total heat generated by the system during operation extremely low. The Fermilab IARC team is aiming to achieve low thermal loading by integrating 4 independently demonstrated, patented technologies into a single energy-efficient system. They utilize niobium SRF cavities coated with tin, which increases the superconducting cavity's operating temperature and aligns it with the cryogenic cooler's operating range. They embed the electron source, the beam gun, directly into the cavity, effectively minimizing the amount of external heat that can leak into the superconducting cavity system. The coupler, designed to transfer radio frequency power into the cavity, is engineered to minimize heat entry from the outside. Additionally, they employ conduction cooling with the commercial cryogenic cooler and an aluminum connection to the SRF cavity. This system efficiently accelerates electrons to the energies needed for powerful X-ray production. Particle accelerators offer significant flexibility for solving commercial applications but bring a level of complexity. An accelerator requires numerous devices to control and monitor performance, working together seamlessly. While most of these devices by themselves are not complex, integrating them is akin to orchestrating a symphony. This orchestration is tamed by integrating the accelerator with the right control system. Most control systems used in large-scale particle accelerators are traditionally unwieldy and incomplete out of the box, requiring extensive IT department resources for implementation. This significant investment is not viable in the commercial sector. The Blinky-Lite integration platform provides a superior alternative. Designed as a full-stack solution, Blinky-Lite is ready to deploy immediately. It installs in under 15 minutes and is versatile enough to be deployed on devices ranging from a Raspberry Pi to large-scale cloud solutions. Packaged in Docker containers, it offers exceptional versatility and portability. Blinky-Lite was specifically chosen for the Fermilab IARC accelerator for its secure remote access capabilities. Unlike big science accelerators that have on-site experts available for rapid troubleshooting and repairs, commercial accelerators lack extensive on-site maintenance. Remote experts must be able to identify potential issues before they arise and effectively troubleshoot them. Blinky-Lite is built from the ground up with secure remote access as a core feature, making it the ideal choice for this purpose. Arguably, the most difficult task of implementing a control system is building the hardware interfaces. The hardware interfaces are the no man's land of control systems. On one side are the engineers with volts, bits, and bytes, and on the other side are the software engineers with strings, floats, and ints. Blinky-Lite builds a bridge over the interface no man's land with a number of universal hardware interfaces based on commercially available hardware that can solve almost all of the engineer's needs without deploying armies of experts. The new Fermilab iArc Accelerator is at the forefront of accelerator engineering, but it's still under design and fabrication. Given its cutting-edge nature, engineers need to perform crucial tests and measurements as the accelerator is being built. This presents a classic chicken and egg situation. You need the control system to test the components during construction, but traditionally, the full control system isn't ready until the entire accelerator is complete. This often leads to a mad scramble during final commissioning. That's where Blinky-Lite comes in. Its quick installation lets the control system grow alongside the accelerator during fabrication and testing. To evaluate the critical technologies for the main accelerator, we built a dedicated test stand. This stand consisted of several key subsystems: a superconducting cavity inside a cryostat, a vacuum system to pump down the cryostat, a cryogenic cooler for cooling the cryostat, instrumentation for measuring temperatures, vacuum levels, flow rates, and managing interlocks, an RF system to control the frequency, phase, and amplitude of the radio frequency in the cavity, a machine protection system (MPS) to monitor and prevent damage. Let's start with the vacuum system, which is essential before any other components can be added. You can't cool down the accelerator until the cavity is pumped down. Our test stand vacuum system is relatively simple, requiring a roughing pump and a turbopump to pull the vacuum low enough to turn on the cryogenic cooling. We used a labeled Turbolab 450 cart, which includes a digital I/O and analog interface. Normally, standard vacuum control uses PLCs, programmable logic controllers. However, commercially available PLCs present challenges. Purchasing the right hardware and software takes time, and the biggest risk is vendor lock-in. Switching vendors later if the PLC isn't right is difficult. For the necessary ruggedness, Blinky-Lite uses the Controlino, an open-source PLC. The Controlino offers rugged housing, relays, 24-volt digital and analog I/O, yet it can be programmed with the open-source Arduino IDE. This open-source choice allows us to easily control the vacuum system with other open-source PLCs and, more importantly, version the code for documentation. We developed an interface between the Blinky-Lite control system and the Controlino by simply providing a straightforward map between the database and the PLC controls. Once the low-level software was done, we developed a Blinky-Lite app to measure pressure, control the pump, set vacuum limits, and receive notifications if something goes wrong. The compressor package for the pulsed tube cooler features an Ethernet interface that responds to Modbus commands. The entire Modbus table is integrated into the Blinky-Lite control system through the standard Blinky-Lite Modbus interface. A comprehensive control application has been developed to display temperatures, pressures, flows, and digital status. The application provides the capability to enable or disable the cryogenic cooler efficiently. Now we will take a look at the instrumentation needed for the test stand. Most accelerator instrumentation deals with rather mundane but extremely important functions such as measuring temperature, monitoring cooling flow, scanning vacuum pressure, and a host of other long-time scale or slow processes that protect and ensure that the system is operating within normal conditions. Since the mid-2010s, there has been an explosion of low-cost, high-performance microcontrollers. These microcontrollers are small computers on a single chip, containing processors, memory, and I/O ports to control specific tasks in embedded systems. Most of these microcontrollers support I2C and SPI protocols, unlocking a vast array of commercial instrumentation daughter cards that are ideal for developing instrumentation for particle accelerators. The Blinky-Lite instrumentation suite, based on the Raspberry Pi PicoW microcontroller, is designed to handle long timescale processes commonly encountered in control systems. Its hardware and software design are fully open source. The suite includes multi-channel sensors, such as a 4-terminal resistor measurement for cryogenic temperature measurements, a high-precision temperature probe, a 3-channel K-type thermocouple probe, a large area water leak detector, a 20 mA current loop sensor, a 12-bit ADC, a versatile interlock system for motion, thermostat, and closure sensors, and a thermal camera based on the FLIR Lepton chip. With the instrumentation in place and the cavity pumped down, we get to the heart of the test stand, the low-level RF LRF for short system. This is also the center of the machine protection, as the cavity is the most temperamental or fragile component. The superconducting cavity we're using is a test cavity, not the final version, and was used to measure material properties. For the material property measurements, the test cavity coupler was designed to be lightly loaded, resulting in an extremely narrow bandwidth, less than 1 part in a billion. The test cavity is also lightly supported in the cryostat to minimize the thermal load for conduction cooling, leading to strong microphonic vibrations driven by the cryogenic compressor. Finding the resonance of this test cavity is incredibly difficult. Successfully implementing a driven LLRF system for this narrowband test cavity will ensure we are well prepared for the higher bandwidth final version, where the final accelerator cavity will have a bandwidth several hundred times wider and enhanced microphonic damping. LRF systems require prompt and reproducible controls, making field programmable gate arrays (FPGAs) the typical choice for signal processing. The current trend is often a contest of who has the biggest, most complex FPGA. We chose a different path. This system must be robust enough for industry and can't rely on a temperamental, high-cost, or hard-to-repair platform. Therefore, we chose a commercial Red Pitaya STEMLab 12514 platform. This credit card-sized RF signal acquisition and generation platform is available for under $700. This platform features two 125 megasamples per second 14-bit inputs and outputs. It is built upon the Xilinx Xeon 7010 system-on-chip architecture and provides remote access via Ethernet or Wi-Fi. The Red Pitaya operates on a 5-volt DC power supply and consumes approximately 1 watt of power. The complete low-level RF system consumes less than 8 watts of power and weighs less than 1.2 kilograms. The system has been rigorously tested on the prototype superconducting test cavity. Driven phase lock to the cavity was achieved at over 3 megavolts per meter. The system measured strong microphonic vibrations exceeding 30 times the cavity bandwidth. Despite these significant microphonic vibrations, the amplitude was regulated to within 0.5%, and the phase was regulated to within 0.2 degrees. With the LLRF system in place, our attention turns to the MPS or machine protection system. The MPS is a very good example of how you can add custom automation to Blinky-Lite. The MPS is a vital system that safeguards fragile accelerator equipment, such as the superconducting RF cavity. This system must be robust, flexible, and designed for long-term operations. The core machine protection strategy is divided into 2 prongs: slow protection and fast protection. The fast protection system operates on a timescale of microseconds to 50 milliseconds. For a compact superconducting accelerator, this is primarily handled by the FPGA in the LLRF system to address events like superconducting RF trips or quenches. The slow protection system is customizable and handles events on a timescale greater than 50 milliseconds. Most protection is serviced by the slow system. It's designed to catch common issues like cooling, vacuum, and system failures, and even setting errors. The customizable nature of the slow system is key. It allows operators to add features long after the initial design and commissioning. The slow machine protection system is built on the Blinky-Lite hierarchical architecture. It uses named values called cubes, which often store scalar data. Attached to a scalar cube is an alarm block. This block defines 4 key limits. Low and high settings act as warning limits. The low and high settings are the error limits. Cubes are organized into trays which contain information for a specific subsystem, like a vacuum pump. Device data is sent to the tray process via various interfaces. This tray data is then published via MQTT to a box application. The box checks the data for alarms and sends the alert to the notification server and the alarm viewer. The core of the machine protection is a process on the box that listens to this MQTT feed for tray updates. This process scans the trays for alarms. If a tray enters an alarm state, or if the tray hasn't been heard from for a set period, an action switch is notified. The power of this system is that custom actions can be added graphically to this switch. For instance, if a temperature tray reports an alarm, the corresponding function node in the switch executes code to perform an action, such as turning off the LRF system. Thanks to the publish-subscribe nature of MQTT, these actions are immediately sent to the action tray, without delay from polling or database access. Finally, a crucial step in the process is automatic documentation. In addition to sending out the actions, the settings are immediately logged, and a log entry is automatically created in the post-mortem log. This log captures not only the event, like an alarm for a temperature sensor, but also the specific actions that were taken by the machine protection system. This makes diagnostics and future analysis very straightforward. This wraps up our Blinky-Lite case study of the Fermilab IR compact accelerator technology. The new energy-efficient electron beam accelerator at Fermilab IARC, which integrates SRF cavities and commercial cooling, is essential for transitioning particle accelerators into compact commercial applications, such as safer medical device sterilization. This complex system's commercial viability is ensured by the Blinky-Lite control system. Blinky-Lite is a full-stack, immediately deployable solution that provides secure remote access and universal hardware interfaces for reliable operations. The accelerator test stand at Fermilab IARC has successfully demonstrated the system's effectiveness, utilizing cost-effective open-source solutions and commercial platforms for robust control. The successful integration of this advanced SRF technology with the robust Blinky-Lite platform represents a significant advancement toward commercial success. Thank you for watching.